Hi everyone, in this video I'd like to work through an application that is going to require us to solve an exponential equation. So I'm hoping these applications actually feel somewhat familiar. They should be really similar to the sort of stuff that we did in, what section was that? 3.3, exponential functions. So let's just go ahead and get started on this one. The setup shouldn't be anything terribly new, but I did pick kind of a messy one, so we'll work on it. Okay, so in this situation, we have a drug being eliminated from the body through urine. 20% of the drug is eliminated every 3 hours after it's administered. So first thing, we're supposed to write an equation giving the amount of drug in the body as a function of the time since the dose was administered. So let's see, every 3 hours. I'm going to say T is the number of hours since administered, and then 20%. Let's say A is the amount of drug, and I don't have units here, but that's fine. So far it doesn't look like I need them. So I'm looking for a function for A of T, and here's what's a little weird and tricky in this one. I don't have an initial amount, so I'm just going to go ahead and use a variable for that, and here's one you can use for free without defining anything new for me. If you want to go ahead and use the variable that represents amount of drug and put this little subscript 0 on it, that's a really common variable for people to use for initial amount of whatever A is. So this is the initial amount of drug. You could read that A sub 0 or A naught even. Turn my phone off and now my baby monitor beeps. Everything wants to beep when I'm making videos. Okay, so again, this is just a variable representing initial amount of drug. We know that whatever we're starting with, it's decreasing by 20%, which means we're ending up with 80% of what we started with every 3 hours. So this would be our setup. So starting with initial amount A naught, decreasing by 20%, ending up with 80% once every 3 hours. Part B is where some solving is actually going to happen. We're supposed to estimate the half-life of the drug, and then we're going to use that to write another equation that represents what's happening. So we have this one that tells us very clearly that we start with A naught, we decrease by 20% every 3 hours. We're going to build another one that shows us the half-life very clearly. Okay, so once again, we don't actually know the starting amount, but it doesn't turn out that it matters. If you want the half-life of the drug, you're trying to figure out how long it takes for the initial amount to get cut in half. So we want to know when this is going to equal half A naught. Okay, so we do have this extra variable. We're solving for T. Half-life is time it takes to cut in half. But the A naughts end up not giving us any trouble because your very first step can just be to divide both sides by that A naught, and you're left with 1/2 equals 0.8 to the T over 3. We should now take a log, and you can really choose any log you want. I would actually say for a word problem, this should probably be dictated by your calculator. If it's easy for you to choose a log base other than 10 or E, then go ahead and just use log base 0.8. That's going to solve this with the least amount of S. I have a calculator that it's easiest to use a natural log or common log in, so I'm going to go ahead and use natural log here, just to save me from having to change base in order to plug this into my calculator. Okay, so I'm taking the natural log of both sides. I'm going to then move the T over 3 down to the front. Let's go ahead and divide by the natural log of 0.8. And then we can multiply it by 3. Okay, And then I would like to get an approximate answer from my calculator. That is an exact answer, but for word problems, I'd always like us to think about the kind of answer that's going to be most useful for somebody who would ask this question. And I would say that most people probably would want a decimal approximation here. So we're going to go ahead and use the natural log button down here right next to the number 4. 1/2 natural log. Okay, make sure you don't try and cancel out natural log. Natural log on its own is not a number, it's a function, so it doesn't cancel. These are not attached by multiplication, so we do have to type that whole thing in, and I'm getting approximately 9.32, and this is time in hours. The other part of part B was to decide, let me see, write another equation representing the situation. So what I'm claiming right now is that this 9.32 is the half-life, which means it takes 9.32 hours for this thing to get cut in half. If I want to write an equation that more clearly shows that, let's see if I can squeeze it in here. I still don't know a starting amount, so I'll just use that A0. If it's getting cut in half, I'm going to use a base of 1/2. And if it's doing that every 9.32 hours, almost fit it, pretend like that fit. You'll have a T over 9.32. Again, sorry for this. This is a T over 9.32 in the exponent. Starts at A0, gets cut in half every 9.32 hours. Okay, last question. If the initial dose is 10 milligrams, how much remains in the body after 24 hours? This actually doesn't sound like it requires any solving. I'm being given an A0 and a T value. So I have 2 equations to choose from. I'm going to choose the one from part A. The reason for that, T is in hours, is because when I wrote this equation that shows the half-life, there's some rounding involved here. This 9.32 is approximate, so I've lost a little bit of information. It's still pretty good, but the first one is a little bit more exact. Okay, so using the first equation, I'm starting with 10 milligrams, multiplying by 0.8 to the T over 3. 24 over 3 is 8. So 10 times 0.8 to the 8, 1.68-ish. And if we started with milligrams, we should be ending up with milligrams. All right, thanks for watching.